So hello guys, welcome. In this video we are going now to talk more about the whitewater simulation parameters and how to control the whitewater log. So I've created this simple simulation in order to test the different parameters in our whitewater simulation, and actually I needed to create a simpler simulation than our fluid crash because this simulation here will give us the capability of testing the parameter fast without the need of a long time simulation. Okay, so this simulation is just a sphere moving in water like this, and I've just created this from the shelf tool, and I've created the whitewater simulation from the shelf tool as well. So we have talked about the whitewater scale, the voxel size, the velocity offset, emission amount, and the aging rate, which is the rate at which the particles reach their lifespan. So whenever you just increase this parameter, your whitewater will age more quickly, okay, and they will reach their lifespan quicker. So when you just increase the lifespan, the aging rate of the bubbles, they will convert into foam more quickly. Okay, we have talked about the limits, and actually we didn't talk about this depth range parameter. And this depth range parameter is just this parameter here just represents the distance from the surface of our liquid. So here we have set it to 0.8, which means 0.8 meters from our liquid surface. Okay, and this distance from our surface will be just used in anything here controlled by depth. So when you just see in the forces tab, you have buoyancy by depth, you have advection by depth, you have multiplier by depth. Okay, so those parameters here controls those forces, and we'll talk more about them in the next videos. So you control this buoyancy force by depth. So here in this ram parameter, the particles at a depth of 0.8, which means particles that lie 0.8 meters over our liquid surface, will have a buoyancy of 1, and particles with the distance, or the depth range of negative 0.8 will have a buoyancy of 0. So this parameter here applies a range from 0.8 to negative 0.8 to those ramps here. So you can control the particles that lie 0.8 meters outside our surface. Okay, and here you can also control the particles that lie 0.8 meters inside our surface or under our surface. So if you just create a grid, and this grid is okay, let me go inside this grid and hide other objects. Okay, so if this is the surface of our liquid, a depth range of 0.8 offers a range from 0.8 meters above the surface, and a range from about 0.8 meters above our surface to negative 0.8 under our surface. So if we go to this view, this is 0. Okay, this is about 0.8, this is about negative 0.8. So 0.8 above our water surface, negative 0.8 under our water surface. So you can control the particles at these two values here, and you can control the particles in between. So here is 0.8 and here is negative 0.8, and you can control this range by this parameter. Okay, I hope this is clear. So it seems somehow complicated. So this is just a range or a span of negative 0.8 2.8, and you apply this range to those ramps here. Any ramp here that have this any ramp here that had this word by depth, control the particles within this depth range. Okay, now in this foam tab here, we have more advanced controls here. We have clumping, which we are going to talk about in this video. Okay, and we have erosion, we have repellents, and adhesion. Okay, we are going to talk about these in details, but in this video we are going to talk about clumping. So here we have also density control, but now we offer the depth range by 2 values, not only by 1 value. So particles within this depth range of -0.75 and 0.25, particles in this range will just undergo the clumping forces that we are going to apply by these parameters. So the meaning of clumping force, or this constraint stiffness here, is the ability of the areas that have dense particles to clump and constrain themselves. Okay, so whenever you have a dense area of particles, those areas will tend to constrain or to apply constraints, and this will give our particles more clumping look. So this constraint stiffness here controls how strong our particles will constrain their movement and just make the clumped areas. Okay, and here you have neighbors, and this controls how will the particle interact with its neighbors in order to do the clumping. So if you just increase the neighborhood size, this is the size of the area of the clumping. So when you just increase this parameter, you will have more area of clumping. So here you have 20 meters, or a circle of 20-meter radius around the particles. Okay, so in this circle, if you just imagine a particle here, okay, you will have a circle of 20-meter diameter around the particle, or 20-meter radius. Okay, and the neighbor particles in this circle will be clumped or will be constrained to our particle here. Okay, so if you just increase this will increase the area of clumping, and more particles will be clumped to each other. And also here is the maximum number of neighbors. You here just define the number of particles that will be clumped within this circle. Okay, so those two parameters here are related to the neighbor particles. And actually you have this inclusion chance. If you just set this to 1, the chance of the particles in the circle of the 20-meter radius here to be included in the clumping constraints will be 100%. Okay, so if you just decrease this, less particles will be clumped within the radius here that we have set. Okay, and actually the constraint iterations are the number of constraints will be made with each neighbor. So if you just make this 5 constraints will be made with each neighbor. If you just increase this, more constraints will be made and more clumping will be made. And maximum acceleration, this maximum acceleration is the maximum change of velocities that can happen to the constraint. So when you just decrease this, the particle will be clumped more and will have less freedom to move within their constraints, so they will look more clumped. Actually, when you change those parameters, you may not notice anything, and the change will be very slight. But I will show you a comparison between 2 different settings and those parameters, and you will see the slight difference. Actually, I don't use those a lot in our simulation, and you can try those parameters and try to reach something that looks good for you. Okay, so here we have this tensile radius. This is the radius, the radius at which the particles will just undergo a repulsive force. So when the distance or the radius between two particles is 0.1 or less, those particles will repulse from each other, and this actually decreases the clump. So this parameter here is just the opposite effect of clumping, and actually this makes sense because you don't want the particles to clump a lot, and you need just some opposing repulsion here when the particles reach a very close distance to each other. This distance here is set to 0.1. Okay, and the tensile strength is the strength of this repulsive force when the particles get nearby each other. Okay, so this won't make sense until we just show an example, and actually the change here will not make sense when you just change the number by different small values. So what I have done is that I made an example of the default values here, and I made another example here with different values. I have set this constraint stiffness to 50 and the neighborhood size to 100, and I have changed the maximum number of neighbors to 500, the constraint iterations to 50, the tensile radius to 1, the tensile strength to 5. Okay, so the stiffness will make the clumping very strong. The size of the clumped areas will be something very big. Okay, I've set it to 100, and the and more particles will be clumped. The maximum number will be 500 particle. Okay, actually the constraint iterations I have set it to 50 in order to make very strong constraints. So the more constraints you have, the more strong clumping. And I have made also a strong repulsive force, because I don't want all my particles to constrain with each other. I want this sort of repulsion that will happen between different nearby or very near particles. So I have increased the tensile radius to 1 in order to have more repulsion, so the particles don't have to get very near to each other to have repulsion. Okay, and I've increased the tensile strength to 5, so I have now more repulsion. So let me show you this example and the comparison. And one thing before I show you is that here those parameters here corresponds to a node called pop fluid. So if you just create a pop simulation or a simple pop simulation and try this node, which is called pop fluid, you will see those parameters, and this node actually tries to give the particle simulations, like this white water simulation, the look of water or the look of fluids. So when you just see waters, the water droplets tend to clump in areas and tend to make some constraints. They are not just like simple particle simulations, and not each particle is separated from their neighbors. Okay, so I just encourage you to apply this particle or this pop fluid into your particle simulations and try different values and your parameters, which will make the parameters look more sensitive, or I should say the parameters will make more sense to you. Okay, so let me show you the example. So here in the right side is the parameters, is the test with the parameter change that I have told you, and I've increased the clumping. And on the left side here we have the default parameters. So if we just compare at frame 80 for example, okay, you will see here our particles are more clumped to each other, okay, and the cellular locking here and the separation is not available anymore. And also some of the particles still have this cellular locking because we have repulsive force for the nearby particles, and actually you still have more particles here separated because you still have repulsive force. Actually this change is very aggressive because I wanted you to see the clumps, because if you just change the values by small numbers, you will have a very slight change here and you will not see the clumping. Actually you can change the frame of comparison in order to see more change here. Actually you see more clumps now, and this gives our particles more fluid looking, although it's very aggressive. And actually in our simulation I will use the default values. I have made just those changes in order for you to see the these parameters. Okay, so this is the first kind of changes that you can apply to your whitewater simulation. And actually you can also control those things by depth, I think. Actually when you just check on this variable stiffness parameter here, you can control this by depth, and this is the same idea that I've discussed here in the buoyancy by depth and those parameters. So this is for this video. Thank you for watching.